Hey there, curious minds. Welcome back to Mathematical Frontiers, the place where we unravel the intricate tapestries of math and science and peer into the very fabric of reality through numbers and equations. Today we're setting sail through the complex yet fascinating world of neural networks. Let's start with the convolutional layers. These are the sentinels of our neural network, tirelessly sifting through data, finding patterns and features with their mathematical sieves. Imagine them as the cartographers of our digital landscape, drawing borders and highlighting the areas of interest. Next up, we have the max pooling layers. Think of these as the alchemists of the network, condensing knowledge into its purest form. They take the vast information seas and distill them down to droplets of essence, ensuring we keep only what's most vital. And lastly, the fully connected layers. These are the grand synthesizers, the maestros orchestrating a symphony from the individual notes played by the previous layers. They bring it all together, forming the final decisions that let our AI not just see, but understand. As we journey through each layer, remember, we're not just learning how machines learn, we're glimpsing into the future of technology, where math and data coalesce into intelligence. So, strap in and let's delve deeper into the convolutional cosmos, where every kernel and neuron holds the key to unlocking the mysteries of artificial sight. To start with, we will explain the convolutional layer or operation. Here we have our input, a matrix, a grid of numbers representing pixel values in an image. It's the raw data our neural network starts with. Now, meet the kernel, also known as a filter. This little matrix slides over our input data like a searchlight, illuminating patterns by performing an element-wise multiplication with the part of the input it covers. And what we get is this, the output, also known as the feature map. This is where the magic happens. By applying the kernel to our input, we've distilled information, we've highlighted features, we've begun to understand the structure of our data. See this calculation? It's where the kernel has been applied to the central part of the input. We multiply, we sum, and voila! Our output matrix starts to take shape, one value at a time. Each value in this output represents a certain feature or pattern detected by our kernel. It's like each number is a clue to what the image contains, edges, textures, or shapes. This, my friends, is how a machine begins to see. In front of us we have the convolutional operation, denoted by F sub mn. This represents the output value at the mn position on our feature map. Imagine it as pinpointing a location where we've just uncovered a hidden treasure on our map of data. Our treasure map is drawn through a process called the convolution function, S of I, j, which equals the convolution of P and K at the ij position. Here your P stands for our input function, basically our matrix of pixel values, and K is our kernel function, a matrix of weights, acting as a filter to highlight features in the input. The convolution itself is carried out by summing over the product of P sub I minus M, J minus N and K sub Mn across all values of M and Ne. This is the sum of the input values multiplied by the kernel weights, sliding across the entire input array. And that's how a convolutional neural network begins to see. Through this elegant mathematical operation, we transform raw data into a meaningful structure for analysis. Let's visualize this. We have our input matrix, a 3 by 3 grid of numbers. Picture this grid as a landscape of information, where each number is a feature of the terrain. Watch closely as our yellow rectangle, the pooling window, begins its journey across this landscape, It slides over the grid, moving from left to right, top to bottom, pausing at each 2x2 area to take a snapshot. In each position, max pooling operates like a camera, zooming in on the highest value in the window. Here, as it covers the bottom right 4 numbers, it finds the number 9, the peak of this small region. As a result, in our output matrix, the number 9 is captured as the maximum value, the standout feature among its neighbors. This sliding and capturing process repeats across the entire grid, each time selecting the maximum value within the window. This creates a new, condensed matrix that retains the most significant features from the input. By reducing the size of our data through max pooling, we're equipping neural networks with the ability to be efficient without losing sight of what's important, the prominent features that will help in making accurate predictions. On our screen is the formula that represents max pooling. Let's decode it together. F sub ij is our max pooling output. It's the result we get after applying the max pooling operation to our input pixels. The max function is where the operation gets its name. It looks through all the values in a particular window of our input and selects the largest one, the maximum. P sub I times S sub x plus m j times S sub y plus n represents the input pixels being considered. The I and j denote the position within the input, whereas sub x and s sub y are the strides in the x and y directions, respectively. These strides determine how far we jump across the input matrix each time we move our window. The stride, denoted by S, is like a step size. If our stride is 2, we move 2 pixels over for each step as we slide our window across the input. Through max pooling, we reduce the dimension of our input, simplifying the information while retaining the most significant features. This makes our neural network more efficient and less prone to overfitting. On our screen, we see a diagram illustrating a fully connected layer. It's a network of neurons on the left, each represented by a blue square, connecting to the output layer on the right, shown by the red squares. Every neuron here is connected to every neuron in the next layer. These connections are the information highways of our neural network, where data travels and transforms. The fully connected layer's job is to take all the features learned by previous layers and combine them to form the final output. It's like gathering all the puzzle pieces to see the big picture. Each neuron acts as a decision maker, weighing the input it receives, summing it up, and then passing it through an activation function to contribute to the final result in the output layer. This layer is critical because it integrates local and global patterns learned by the network into a cohesive whole, leading to decisions or predictions. It's the brain's final step before making a move. On the screen is an equation that models the output of a neuron in such a layer. Let's decipher it together. F sub ji is the output of our neuron ji. It's calculated using a special function sigma, which is often a type of activation function like the sigmoid or ReLU. This function sigma takes in a sum. Now, this isn't just any sum. It's the weighted sum of all the inputs to the neuron, represented by x sub I, where I ranges over all the inputs. Each input is multiplied by a corresponding weight, w sub ij, which determines the strength of the connection. But wait, there's more. We also add a bias term, b sub j, to the sum. This bias allows the neuron to adjust its output independently of its inputs, offering an extra degree of freedom to our model. Together, these elements form the computation of a neuron in a fully connected layer, transforming inputs into an output that serves as a complex decision or prediction. And that's how a network synthesizes knowledge and makes intelligent decisions. Let's put all the layers previously discussed with a concrete example. On our screen is a schematic of the LaNet 5 architecture. It begins with an input image of size 28 by 28 pixels. This image enters the first convolutional layer, undergoing a convolution operation with a 3 by 3 kernel with a stride of 1. The result is a feature map with 32 distinct features. Following the convolution, we enter the realm of max pooling. With a 2 by 2 window and a stride of 2, this layer downsizes the feature map to 14 by 14 while keeping the most prominent features. Next, we have the second convolutional layer, which applies another convolution and increases the depth to 64 feature maps. It's followed by another max pooling step, which further reduces the spatial dimensions to a 7 by 7 grid. The LaNet 5 architecture culminates in 2 fully connected layers after flattening the pooled features, leading to a softmax classifier that outputs the final prediction. Contrary to what we might typically see, this network uses average pooling layers as well as max pooling, which is an interesting design choice from its era. This architecture laid the groundwork for modern deep learning, proving that convolutional networks could effectively recognize patterns in visual data. And that wraps up our first high-level flight over the landscape of convolutional neural networks. What we've seen today is just the beginning, the tip of the digital iceberg. Stay connected with us on Mathematical Frontiers as we dive deeper into the realms of artificial intelligence and unravel more complex mysteries. There's a whole universe of knowledge waiting to be discovered. So, make sure you subscribe and hit the notification bell to journey with us into the next episode. Much more is on the horizon, and we promise you won't want to miss it. Stay curious, stay tuned, and until next time, keep exploring the frontiers of mathematics.